All right, welcome everybody. This is TSI Math Crash Course Day 2, Part 1. Just getting started here. We're going to start with some questions from the homework. Those of you joining us on the recording, again, this is a really small class, and we have Jackson here with us today going over all the questions. So anyway, Jackson, I'm going to start with question number 9. This was from the homework. Go ahead and read that question, and we'll go over it together.
Okay. How do you?
Yeah, I think this would be actually pronounced Xiaoming. Xiaoming. But you can say X if you want.
Ming is making cookies. Each batch of cookies uses 3 eggs. If Xiaoming has 20 eggs, and assuming he has enough of the other ingredients to make the cookies, what is the greatest number of batches that he can make?
What is the greatest number of batches that he can make? Okay, now I think the temptation here is like to do some operation with the numbers. You know, we've got a 3 and a 20. Maybe we can do something with those. You know, I don't want to worry. I just want to think purely logically here, right? Purely logically. And this really goes back to sort of the rules for math that we'd gone over previously. And I may have to refresh this here. In fact, I'm going to do that. One of the rules is just using basic logic. And I want to do that. This should load here in just a minute. All right, so he's got 20 eggs, but he needs 3 eggs for each batch of cookies. Okay. If you're going to give me an estimate right now, don't even worry about the answer choices right now. If you're just going to give me an estimate, just talk about pure logic here. How many batches do you think he can make?
6.
6 sounds pretty good. How many eggs is he going to need for 6 batches of eggs? Or 6 batches of cookies? How many eggs?
3.
Yeah, there'd be 3. 3 per batch. So yeah. How many eggs total?
3 times 6 is 18. 17.
Yeah, 18.
Yeah.
Could he make 7 batches of eggs?
I guess he probably could, but
well, how many eggs does he need if he's making 7 batches of cookies?
He needs 21 eggs.
21 eggs. Does he have 21 eggs?
No, he doesn't.
No. So he can't make 7 batches of eggs. So it's got to be 6, which is what you said, right? Good. I mean, and look at the answer choices now. Right? I mean, obviously, answer choice B is looking pretty good, just logically.
Yeah.
But we could eliminate A. A is silly. Right? He can make more than 3 batches of cookies with 20 eggs.
Yeah.
Right? He could make 3 batches of cookies with 9 eggs, and he's got twice that. So it's not A. Answer choice D. Look at answer choice D.
17.
17.
Yeah, that's a little.
Yeah, that's like if it only took 1 egg per batch, maybe he could do. But no, that's 3 eggs per batch. There's no way he'd need like 50 or 60 eggs, and he just doesn't have that much. So it's either B or C. And again, logically, we just kind of figured out it was answer choice B, which it is. Now here's why I think this is an interesting question. Is that if you just kind of focus on the operation, not the logic of it, but if you're like, oh, 20, I'll just take the number of eggs and divide by the number of eggs per batch, right? You get 20 divided by 3. And what's that?
20 divided by 3?
Yeah. Can you do that on a calculator real quick?
Yeah. That's 6.6666.
Yeah, 6.66 for infinity, 6.667 basically.
Yeah.
Which a lot of students be like, okay, I'll just round that up to 7. So the answer's 7. No! A lot of kids are going to answer C on this one. A lot of kids. Does that make sense why a lot of people are going to see that 6.67 and round up?
Yeah, it does.
Don't do that.
Yeah.
Don't do that. And that's why I say don't think in terms of operations. Think in terms of logic. Okay, I know I can make 6 because that's going to take 18 eggs. But if I'm going to do 7, that's going to take 21 eggs. Right? And you can figure that out with logic. If you're focused on the operations, you're going to end up with something like 7.
Okay.
Does that make sense?
Yes.
Okay. Good. Let me see if I have my rules for mathing loaded now. My browser crashed out right before the session, so I think I may have lost this. Let me see if I can bring it up real quick. Well, we'll come back to that. If I don't get it, it's not the end of the world. Oh, here we go. Come on, Google. Do your thing. Well, it's pooping out right now. That's all right. We may have to come back to that, though, later. Okay. Let's go to the next question. I'll clear the whiteboard. And you got the answer for that one. You got B, is that correct?
Yes.
Okay, good. Did you do that? Did you kind of feel that one out logically on that one, or how did you solve that?
I think I kind of mostly just did math. Like,
yeah,
how many times can 6 go to?
But you didn't round up, right?
I did round up.
Well, you didn't round up, right? You didn't round up from 6.67, right? Yeah. So.
No, I just saw that. And I was like, okay, that's obviously the answer.
Yeah. Okay.
It's not the other ones.
Yeah. Good. All right. I like this question. This is pretty easy, I think. But let's go over it. All right. So go ahead and read question number 2 for me, please.
If a club has 36 members, if each member donates 12 items for an auction, how many items will there be in this auction?
Okay.
In the auction.
Okay. Let's think through this one logically, too. Okay, because, there's an operation. This question is begging for a specific operation. We're going to get to that. Let's just talk about it logically here. So, the club has 36 members. Each member is donating 12 items per auction. Okay. Let's say each member was donating 1 item for an auction.
Mm-hmm.
How many items would they have?
36
36.
items.
36, right? 36 members, 36 items. If it was 2 items per auction, or for the auction, 2 items per member, how many items would there be in the auction?
82?
You're right at first. 72.
72.
Right, because it's just 36 times 2.
Yeah.
Right, 70. Okay. All right. If it were 3 items per member, how many items are we talking about here?
90, 100, and,
it's going to be over 100.
100, huh?
Yeah, it's going to be over 100.
Yeah. 108.
108. That's if each member donates 3 items, not 12, right?
Right.
I think right off the bat, just logically here, we can pretty easily eliminate 2 answer choices. What answer choices?
We eliminated A and B.
A and B already, because they're too small.
Yeah.
They're just way too small. We're talking 12 items, not 1, 2, or 3. So it's either C or D. But I think we know now through the logic, the just using sort of the logical approach, we know the operation now. What's the operation? What are we gonna have to do to find out how many?
You have to multiply 12 by 36.
It's just 12 times 36. That's all this is. It's just 12 times 36. Now, I'm guessing here you wouldn't be able to use a calculator. Okay? Because, again, this is from the previous section on arithmetic. You'd probably have to work this out, work out the arithmetic. Do you think you could do that right now?
Yeah.
Okay, let me see you do that then. But again, even if you don't know the exact operation, we know it's either C or D, even if you're just guessing. Does that make sense?
Yes.
Okay, all right. But let's try to carry out the operation now.
On the whiteboard?
Yes, please. That'd be great. Good. 36 times 12. Good. Looking good, looking good. 36 times 2 is 72. And then there's a 6. And hold on just a second, hold on. Oh, okay, I got you now. Yep, you're good.
Okay.
You're good.
432.
There you go. There's your answer. Any questions about that?
No.
Okay. But I'm guessing there's going to be some students that are still going to struggle with going through those steps of multiplying numbers bigger than single digits. And even if you do struggle with that, you still logically know it can't be A or B. You're just guessing between C and D. I'll take that. I mean, it's certainly better than just picking something random.
Yeah, it is.
But you know the operation, so there's no problem. Okay, good. Let's do the last homework question. Did you get that also for the homework? You got D for that?
Yeah.
Okay,
Mm-hmm.
Good. Okay. Go ahead and read question number 4 for me, please.
A conference planner has put together 280 binders for attendees and another 31 binders for presenters. How many total binders did the planner put together for attendees and presenters?
Okay. Do you understand the question here, Jackson?
Mm-hmm.
Yeah. I mean, it's just how many binders total do we have, basically.
Oh,
That's all.
Yeah.
That's all. Okay, look at the answer choices, Jackson. I mean, this question is almost hilarious. Okay?
Yeah.
Look at answer choice A. Why do we know it's not A?
Because the first number they give us is greater than that.
Yeah, the first number is 280. We got 280 binders for attenders, another 31 for presenters. If we're talking about the combined number, the total binders that the planner put together for both, it's not going to be less than 280. That's insane. So A is gone. What about B?
B is gone.
B is gone. Same thing. It's less than 280.
Yeah.
It's less than 280 is crazy. Just logically. What about C?
I think C would be the answer.
C's reasonable. And C's looking at, that's without doing any arithmetic here, right? That's without doing any addition, which is ultimately what we're going to have to do. But just logically, just feeling that one out, that's at least reasonable. What about answer choice D?
That's completely not reasonable.
That's not a reason. They're not even close. That's like double 280. More than double 280. There's no way I'm going to get 280 binders and combine another 31 binders to get that number. Just logically, it's got to be. That's without doing doing one step, doing one operation. We're just feeling that out logically. Does that make sense, Jackson?
Yes.
You don't even need to carry out the math here. I mean, you can. You can. Can you show us real quick, just for anybody that's not certain about, watching this video, that's not certain about the actual, how to add these numbers without a calculator. Can you carry that out for us real quick on the whiteboard?
Yeah, I
Good.
can.
But again, you don't even need to go there.
Shh. Yeah, I got family here.
Yeah, you're good. You're good. Dude, I've got 4 daughters, man. They're 7 and under. There's a good chance I'm going to have to stop and calm things down at some point. All right. Excellent. You got it. Answer choice C. All right. Any questions about that?
No.
All right. Let's see if my Google Drive is working out. Boy, I don't know what happened here to my connection here. Mildly annoying. Oh, something is happening. Let me see if...
Yeah, it's really annoying when it does that.
I don't know what's going on. I can't even get to Google. Okay. Okay. I may have to, because I do want to, we're going to have to go over some of the information I've got on that document. Boy, oh boy. Let me close that out. See if I can just, if you just bear with me for just a minute. Okay. There we go. Come on. There we go. Now we're working. Thanks for your patience here. I just, we're going to be needing this document for some of these questions. Come on. There we go. Okay, that's going to load. Let me go to the next question while that loads. Okay, so next questions are new questions, Jackson. A couple new concepts. Go ahead and read question number 8 for me, please, as soon as that pops up on your screen.
Okay. Which of the following fractions is equivalent to?
Yeah. To that thing.
-9.
Yeah.
Divided by 8.
Yep. Okay. Okay. So how would you read this numerator part of the fraction? How would you read that?
-6. -9.
Yeah, that's -6.
-9.
I mean, that's -6 minus -9. Right?
Right.
Because, I mean, it's -6, and then that's a minus sign, minus -9. Okay? Does that make sense?
Yes.
Now, I know you know that you're supposed to do something when you see two negative signs together. Do you know what you're supposed to do?
Change it to a positive sign?
Change to a positive, yeah. When you're subtracting a negative, you basically turn it to a positive. Does that make sense?
Yeah.
Here's how I like to explain that for some students. Imagine that you have credit card debt. Jackson, do you have a credit card?
No, I don't.
Good. You've got very responsible parents. That's good. All right. I'm glad you know. All right, but let's say you had a credit card, and let's say you had you spent $2,000 on like video games or something like that. So you've got negative $2,000 basically to your name. Negative $2,000. Does that make sense?
Yeah.
All right. If I, from the generosity of my heart, saw that this poor student is $2,000 in debt, and I wanted to take away your debt, I wanted to take away that negative. Yeah? I took away your debt. Gone. Erased it. I've basically given you $2,000. Haven't I? If I took away your debt. You have $0 in your bank account. You have nothing. Right? But if I've taken away a negative, I've basically added $2,000, haven't I?
Yes, you have.
Does that make sense?
Yes.
So we take away a negative. This is the kind of example I used to talk about when taking away a negative. Right? If I take away a debt, I'm basically giving you money. Okay? All right.
Okay.
So how do we take away -9 from 6? What are we doing?
You're basically just adding a positive 9 to it?
Yeah. It's a -6 plus 9. So let's rewrite that. So we got -6 plus 9 divided by 8. Okay. Let's take care of that numerator first. Okay. How do we do that? What's the operation there? -6 plus 9. First of all, is that going to be positive or negative?
That's going to be positive.
It's going to be positive, right? Because that 9, that positive 9, is more positive than that 6 is negative. Does that make sense?
Yes.
Yeah. And if you're the other way around, if it was 6 minus 9, we know it's going to be negative because the -9 is more negative than the 6 would be positive. But positive 9 has a bigger absolute value, right, than the -6. So we know it's going to be positive. Just knowing that this fraction is going to be positive, we can eliminate two answer choices. What can we eliminate?
I'd say the A and C.
A and C. Because they're negative. And we know the right answer is going to be positive. Does that make sense?
Yes.
What's the right answer going to be? Is it going to be B or D?
I think it's going to be B.
It's going to be B, dude. It's going to be B. Just getting to... and all we did is realize that, hey, there's two negative signs there. That means we're adding. That's all we did.
Yeah.
And then we could eliminate the negative ones, A and C. And you realize we're not adding, answer choice D, that would be 6 plus 9. Come on. It's not. It's -6 plus 9. It's going to have to be different. And because that means you're subtracting 6 from 9, which is going to give you 3. So 3/8, which is answer choice B. Any questions about that?
No.
No? It's not complicated, is it?
No.
No. So again, as long as you recognize that when we see two negative signs in a row like that, when you subtract a negative, you're adding. But if you're confused about, what do I do when I subtract a negative? Think about the debt example, right? If you take away someone's debt, you're giving them money. You're adding. Does that make sense?
Yes.
Okay. For multiplication, by the way, it's also the same. If you multiply two negative numbers, like -2 times -3 is +6. Okay?
Okay.
But a negative times a positive is still negative. So basically, 2 in a row, the same sign, becomes positive. Any questions about that?
Nope.
Nope. All right, cool. Let's do the next one. Ooh, this is a little bit trickier here. Hey, question number 15. Go ahead and read this for me, please.
Which of the following values is equivalent to 5 cubed? Negative cubed?
Yeah, I would say 5 to the power of negative 3 is probably what I would say.
Yeah.
Yeah, if it were just 5 to the power of 3, I'd probably say 5 cubed. But that's a negative 3. It's negative 3, so I'd say 5 to the power of negative 3. Okay. Now, have you seen negative exponents before?
Yeah, I was just covering this.
Great. Great. Okay. Now, what do you do with negative exponents? There's a specific operation. You just have to know it here to answer this question.
I think that it's kind of like what's it called? You factor it.
You're not going to factor it.
You write all this stuff out. I thought that's what you did.
No. Oh, you're thinking about taking the cubed root. That's what you're thinking about. Like if we saw the cubed root of 8, what's the cubed root of 8? Right? That's when you factor it. That's when we're like, well, 8 is 2 times 2 times 2. And the cubed root means basically what multiplied by itself 3 times gives you 8. And that answer is 2.
Yeah.
Does that make sense? 2 multiplied by itself 3
times. That was
times.
confusing for me.
Yeah, that's a little tricky, right? The cubed root of 27.
Okay, I actually remember now.
Yeah.
Did you write it out in fractions?
Yeah, you turn it into a fraction. Basically, here's what a negative. Yeah, don't worry about the cubed root. I don't think that's tested on the TSI cubed roots. I haven't seen it that I recall. But basically, when you see a negative exponent, that means basically you're going to turn that. You're gonna take the inverse of that number. So let's start with an easier one. Let's say 2. Let's say 3. 3 to the power of negative 2. Okay. So I know you know what 3 squared is, right? What's 3 squared?
3 squared is 9.
3 squared is 9, right? Because that means 3 times 3. A negative exponent means you take the inverse. You flip the numerator to the denominator. So 3 to the power of negative 2 is the same as 1 over 3 squared, which is 1 over 9. 1 over 9. Does that make some sense, yes or no?
Yes.
Okay. Negative exponents means you're taking the inverse. Have you ever combined exponents before?
What do you mean by that?
Like, let me show you. Like, if we had x to the power of 5 over x to the power of 7. You ever combine exponents?
No, I haven't.
No. Okay.
I may have, but
yeah.
Still.
Don't worry. You know, I was going to go down a certain path. I was going to get all algebraic. I think I'm going to avoid that. I'm going to avoid that right now. But just know this means that it's the inverse of 5 to the power of 3. Okay, does that make sense? The inverse of 5 to the power of 3. So 5 to the power of negative 3 is the same as 1 over 5 to the power of 3. Does that make sense? Yes or no?
I guess.
Maybe you don't understand why it equals that. Is that kind of where you're stuck on?
I don't understand why, but I see what you do.
Yeah. Let me try to explain why. Here's why. Okay. Let's go. I'm going to give you some concrete examples here. I'm going to avoid variables. Let's say 2 to the power of 3 over 2 to the power of 2. Let's start there. Okay. 2 to the power of 3 over 2 to the power of 2. What does that equal?
9 over 4.
2 to the power of 3. What does 2 to the power of 3 mean? What's anything to the power of 3 mean?
2 times 2 times 2.
2 times 2 times 2. And what's 2 times 2 times 2? It's not 9.
8, not 9.
8, right? So that equals 8 over 4 right? Because 2 squared is 4, right? 2 times 2. So 8 divided by 4 is just 2. Okay? Does that make sense?
Yeah.
Okay. Now here's another way to look at this. If you have a like base, which we have here in 2, right? This wouldn't work if there were 2 to the power of 3 over 7 to the power of 2. It's only whereas we got 2 to the power of 3 over 2 to the power of 2. You can combine the exponents by taking the exponent from the denominator up to the numerator and subtracting it. Okay? Does that make sense?
I guess.
Okay. Here's why that works. Like, another way to write out 2 to the power of 3 is 2 times 2 times 2. Another way to write out 2 to the power of 2 is 2 times 2. Right? Does it make sense why this and this are equal? Does that make sense?
Yeah.
Okay, that makes sense. Okay, good. Okay. So, what I can do, I've got the same thing in the numerator as I've got in the denominator. I can start canceling stuff out in that fraction right there. Right? I can start canceling out some of those 2's. I got a 2 up here and a 2 down here. Gone. I got a 2 up here and a 2 down here. Gone. I'm left with just a 2. Which is 2 to the power of 1. Does that make sense?
Yes.
Okay. So just know that whenever I have a like base, like I have here with 2, got a like base, I can take the exponent from the denominator, bring it up to the numerator, and subtract it. Which would give me 2 to the power of 1, which is just 2. But that's the same thing I got here, as I got here, as I got here. 3 different ways of or that last one here. 3 different ways of looking at the same sort of the same operation, but the same question. Okay? Does that make some sense?
Yeah.
Okay.
So there's 3 different ways of putting it.
Yeah, absolutely. And it would work too, like, let me give you another example with the numbers. If it were 2 to the power of 5 over 2 to the power of 3. Okay? Let me zoom out a little bit. Let's do the operation here. We got a like base in 2, right? So I can take the exponent from the denominator, that 3, bring it up to the numerator and subtract it. What's 5 minus 3?
2.
2, right? So it's 2 to the power of 2, and what's 2 squared?
4.
4, okay? That's the same as, another way to look at it would be to say, okay, 2 to the power of 5 is 2 times 2 times 2 times 2 times 2. Over, and then 2 to the power of 3 is 2 times 2 times 2. Does that make sense?
Yeah.
Okay. And look, I can cancel stuff out. I got a 2 in the numerator, 2 in the denominator. That's gone. 2 in the numerator, 2 in the denominator. Gone. 2 in the numerator, 2 in the denominator. Gone. I'm left with just 2 times 2, and 2 times 2, of course, is just 4. But that's the same thing that I got right here. Does that make sense?
Yeah.
Okay, great. So, with that example in mind, I'm going to clear a bunch of space on the whiteboard. But taking that example here in mind, let's look at another kind of fraction. Let's look at 2 to the power of 3 over 2 to the power of 5. Okay? Let's look at that. And I'm going to write it out. I'm going to break down those 2. So it's going to be 2 to the power of 3 is 2 times 2 times 2, right?
Right.
And 2 to the power of 5 is 2 times 2 times 2 times 2 times 2. Well, those 2's cancel out, those 2's cancel out, those 2 cancels out. I'm left with a 1 in the numerator. 1 over 2 times 2, that's just 1 over 4. Does that make sense? Yes or no?
Yes.
Okay. Now let's do the operation. Look, I've got a 2 in the numerator, 2 in the denominator. I've got a like base. I can take that 5 from the denominator, bring it up to the numerator, and subtract it. So 2 to the power of 3 minus 5. What's 3 minus 5?
3 minus 5 is negative 2.
Negative 2. So that equals 2 to the power of negative 2. Does that make sense?
Yes.
And 2 to the power of negative 2 is the same as 1 over 4. right? Because remember, when you see a negative exponent, you just take the inverse, right? Put a 1 in the numerator, 1 over 2 to the power of 2, which equals 1 over 4, as we established. But we also solved it this way here, too. Does that make some sense?
Yeah, it makes more sense than before.
That's why it works. That's why it works. Yeah. But you kind of have to know kind of the properties of exponents first, which we're going to get to a little bit more later. But once you know that you can subtract the exponent from the denominator, bring it up to the numerator, then it's like, okay, that's why negative exponents means the numerator. Basically, it means when you say a negative exponent, it means that 2's in the denominator, and it's being squared in the denominator. That's what it means. Okay? All right. Notice, by the way, negative exponents don't mean negative numbers. Right? We're not even talking about any negative numbers. I mean, we're talking about negative exponents, but not negative numbers. Right?
Right.
Not negative integers. So we can eliminate 2 answer choices just knowing this simple property of exponents, that a negative exponent means the inverse. Not negative. It means the inverse. I can eliminate 2 answer choices right off the bat. What answer choices can I eliminate?
Number C.
Yeah, absolutely. C's gone. And what else?
Number D. I mean, letter
D. You're good. D is gone as well. Absolutely. C and D are gone. So I know we're just not dealing with the negative exponents.
Yeah.
Or negative. I'm sorry, negative numbers. We're not dealing with a negative answer. It's gonna be a fraction, but it's not gonna be negative.
Okay. So just because it's a negative exponent doesn't mean it's a negative answer.
In fact, it's probably not. Unless it was a negative 5 to the power of negative 3, then it could be negative. But even then, if it's negative 5 to the power of negative 2, that's also going to be positive. Even if it's negative 5 to the power of 2, because it would be the inverse of 5 squared. And 5 squared is, even negative 5 squared is still positive, because you got a negative times negative to get a positive. So. Okay, so what's more likely? Do you think it's A or B?
I think it's A.
Okay, so let's talk about what exponents mean. So we know, again, 5, let's go back to the actual question, which is 5 to the power of negative 3. Okay? And we know, again, 5 to the power of negative 3, that means the inverse of 5 to the power of 3. So that means 1 over 5 to the power of 3. Does that make sense? Yes or no? That makes sense?
Yes.
Okay. It means that 5 to the power of 3 is in the denominator, is what that means. So, okay. What does something to the power of 3 mean?
That means you're going to multiply it by itself 3 times.
Multiply it by itself 3 times, which means 5 times 5 times 5. Right?
Right.
That number multiplied by itself 3 times. 5 times 5 times 5. So, 5 times 5 times 5. What do you think is more likely now, A or B?
B.
Probably B. Right? Because A would be 5 plus 5 plus 5. Not 5 times 5 times 5. Does that make sense?
Yeah.
And it is. It is answer choice B. Okay? And it's still, I don't think in terms of operations. A lot of students look at that and they're like, oh, 5 times 3. Well, no, it's not 5 times 3. It's 5 to the power of 3. So think about what the notation means. Think about what that means. 5 to the power of 3 means 5 times 5 times 5. And if I said, hey, what's 5 times 5 times 5? You'd probably be like, well, it's not 15. It's probably got to be 125, which it is. Does that make sense?
Yes, it does.
Okay. A lot going on there, huh? With that question? A lot going on. But again, all you need to know to get the answer right, we know we're not dealing with a negative number because the negative exponent means, or negative answer at least, because the negative exponent means the inverse. So it's going to be a fraction, it's going to be A or B. And then all you have to do is ask yourself, okay, well, what's 5 to the power of 3 mean? And you know it doesn't mean 5 times 3. It means 5 times 5 times 5. So it's got to be B. Logically. Does that make sense?
Yes.
Okay.
Yes.
Good. So be aware of that. There's a good chance they're going to test you on negative exponents. So we're just talking about inverses. That got a little bit more involved than I had planned, but I think it's good nonetheless. And I want you to understand why certain things are. No, I remember as a student, I had math teachers that were like, whenever you see 0 as an exponent, it means 1. And I'm like, well, why does anything to the power of 0 mean 1? And they're like, just know when you see it, that's what you do. And I was like, okay. And that always annoyed me a lot. I wanted to understand why, and most of my teachers couldn't explain why. So I always want to stop and explain why. So I appreciate you. I don't mind you needing a little more explanation. I like it. I like it a lot. Okay.
Yeah.
Question number 11. Go and read that for me, please.
Jacoby followed a recipe that requires 2 cups of water for every 3 cups of flour. If he used 8 cups of flour, how many cups of water did he use?
Okay. I'm going to see. Are my rules for mathing up? Yeah, my rules for math are up. Okay, great. Rule number 1. I want to go over this real quick. Rule number 1, use basic logic and estimation whenever possible. Rule number 2, use process of elimination to test answer choices whenever possible. Okay. So let's do some basic estimation here. I don't want to just carry out an operation. Okay. Let's kind of feel this one out. Okay. So if he uses 8 cups of flour. Okay, well look, I know how many cups of water, I think it's Jacoby, but whatever. This guy, I know how many cups of water he's going to need if he's using 6 cups of flour. How many cups of water does he need if he's using 6 cups of flour?
How many cups of water would he need if you use 6 cups of flour?
Yeah. If you use 6 cups of flour.
Right? 4 cups of water.
4, right? You're just doubling it, right? Does that make sense?
Yes.
Yeah. And I know how many cups of water he'd use if he had 9 cups of flour, right? How many cups of water?
He'd have 6 cups of water.
Yeah, 6 cups of water. Yeah, absolutely. Absolutely. Yeah. 6. Interesting. So if he's got 6 cups of flour, it's 4 cups of water. But if he's got 9 cups of flour, we're talking 6 cups of water. Now, he's not using 6 or 9 cups of flour, he's using 8 cups of flour. Somewhere in between 6 and 9. But I'm guessing the cups of water are then going to have to be between 4 and 6.
Yeah.
Does that make sense?
Yes, it does.
I'm just feeling it out. Just basic estimation.
So because you think that it could be C?
I think C's looking good.
Yeah.
I think C's looking good. In fact, I know it's not A. Why do I know it's not A?
Because that's too small.
It's too small. It's too small. If he's using 6 cups of flour, we know he's already using 4 cups of water. So A is way too small. But even B is wrong. I know B is wrong. Why do I know B is wrong?
Because B would be for 6 cups of flour.
That'd be for 6 cups of flour. And it's not 6 cups, it's more. So it's got to be more than 4 cups of water. It can't be B. Does that make sense?
Yes, that makes sense.
Good. Now, what about 12? How do I know 12? That's answer choice D. How do I know that's wrong?
Because that's too large.
Yeah, it's too big. If he were using 9 cups of flour, he would only need, what did we say? 6 cups of water? Right? We're just multiplying everything by 3, right? So, and 8's not as big as 9, so he's not using 12 cups of water. That'd be more water than flour. And we know it's not more water than flour. It's more flour than water. Right? Just logically. It can't be D. Does that make sense?
Yes.
Notice, we've not carried out one calculation. Do you see that, Jackson?
Yeah.
Not one calculation. So every kid taking this test, except you, and the kid watching this recording, right? They're going to try to oh man, I've got to multiply something, some fraction. They're just going to try to, they do what I call number slapping. They slap 2 numbers together and hope they get something that seems reasonable. But they're focused on operations. Don't focus on operations. Focus on estimation. Estimation. Feel it out. Be like, okay, I don't know about 8, because 3 cups of flour doesn't go into 8 nicely. I don't know what to do with that. But I know how much water I need for 6 cups of flour. 4 cups of water. I know how many cups of flour I need for how many cups of water I need for 9 cups of flour. I need 6 cups of water. it's got to be between 4 and 6, which it is. And that's C. Does that make sense?
Yes, it does.
I don't even want to go over the operation. And I'm going to be honest with you, I'm not even sure what it is right here. But you know what? I don't care. Because that's not the way to look at this test. This is a multiple choice test. And you can figure out the answer using logic and estimation. Okay? It's a way of looking at the questions, man. It's not about operations.
Yeah, it looks like a better way.
Oh, dude, absolutely. Yeah, I mean, because you don't have to learn anything new. Yeah, you got to know. Okay, like the negative exponent, you got to know that. Okay, great. Other than that, like, have I asked you to memorize anything or like study anything yet? Not really. It's just like learning to look at the questions from a logical perspective. That's it. Question number 10. Go ahead and read this, please.
The volume of a right rectangular prism is found by multiplying the length of the base by the width of the base by the height of the prism. The prism. A right rectangular prism has a volume of 30 cubic inches. If the height of the prism is 6 inches, what is the area of the base of the prism?
Yikes. Okay. Hey, do you know what a right rectangular prism is?
No, I don't.
No. It's worth knowing. It's just a shoebox. That's all. It's a really fancy name for a shoebox. Right? It's a 3-dimensional figure. Right? I mean, that's what we're talking about, the volume of this thing. Right? It's got a volume of 30 cubic inches. A square has area, a rectangle has area. But we're talking about volume, it's got to be a 3-dimensional figure. Does that make sense?
Mm-hmm.
It's got to be 3-dimensional. It's a right rectangular prism. I'll bet you could figure it out. Basically means all the sides are rectangles. That's all. So, 3-dimensional figure, kind of like a shoebox. Does that make sense? Something like that. Something like that. Okay. So, the volume of a right rectangular prism is found by multiplying the length of the base by the width of the base by the height of the prism. But you've seen that before, right? You've seen the formula for volume, haven't you, at some point?
Yeah.
Right, the volume goes length times width times height of anything.
Yeah. No, I've done volume.
Yeah, you know that. Yeah. And here it says, this right rectangular prism has a volume of 30 cubic inches. That's the volume. Does that make sense?
Yes.
Okay. The volume is 30 cubic inches. And that says the height is 6 inches. Okay, I'm going to make a note of this. Volume equals 30 inches cubed. And that says the height is 6 inches. So I'm going to make a note of that. The height is 6 inches. Okay. What's the area of the base of the prism? Well, listen, what's going to be bigger? The volume of this shoebox, of this right rectangular prism? The volume? Or the area? What's going to be a bigger number?
The volume?
Yeah, the volume, right? Right, because we get that by taking the base, right, which would be like this part right here, shaded in. Right? That's the base, the area of the base. And then we multiply that number by the height, which is 6, and we get the volume 30. Right?
Right.
So the area, and this is the question. The question is asking us, what is the area of the base of the prism? It's got to be less than the volume, doesn't it?
Yeah, it does, definitely.
Dude, I'm just thinking purely logically here. We can eliminate some answer choices. It's just not going to be it. What can we eliminate?
180.
That's crazy pants. It's not gonna be. It's got to be less than 30. Just lie. I'm not even carrying an operation. I know it's going to be less than 30. That's gone. What else?
I would say 5. Because the height is 6 already, and that's obviously not 6 inches.
What's not 6 inches?
I mean, it's not 5 inches because we see how big 6 inches is on the height of the rectangular prism.
Listen, hold on just a minute, because I think the answer is A. I'm pretty sure.
You?
Oh yeah, absolutely. But I still want to think about it logically. Wasn't I just saying that the volume is going to be bigger than the area of the base, right?
Right.
The volume is going to be bigger than the area of the base. So it can't be C.
Can't be C.
It can't be C. I'm not going to take the base and multiply it by 6 and get something bigger. This is not big. This can't be bigger than 30. It's got to be less than 30. That area. It's got to be less than 30. Because I multiplied by 6 and getting 30. Right?
Yeah.
I'm not going to multiply something by 6 and get some... Yeah. Does that make sense or no?
Yes.
Okay. So I know it's not C. It's got to be either A or B. It's got to be either A or B. Does that make sense?
Yeah.
Okay. Now, part of this maybe... I'm pretty comfortable with area. And I'm pretty comfortable with volume. Okay? And I know that if I take the base of any figure, or like a cone, for example, take the base of any figure. That is an ugly cone. And I multiply it by the height. Actually, that doesn't work with a cone because I got to multiply it by a third. I'm not going to take that example. But for any three-dimensional, like a cube or a right rectangular prism, if I take the area and I multiply by the height, I get the volume. So this question is just a fancy way of saying, if I multiply something by 6, that's going to give me 30. So what multiplied by 6 gives me 30? That's the question.
Yeah.
Does that make sense?
Yes.
Okay. And what's the answer then, obviously?
A.
It's A. It's A, which is true. Okay. And you can see where they come up with these answer choices, which are kind of silly. Like, answer choice B, they just got that you're subtracting 6 from 30. Right. I'm guessing what bothered you about A was that, like, 5 inches for the area? That sounds small.
Yeah.
Right? Was that bothering you? Yeah, but it can't be 24, right? Because 24 times 6 is a really big number. I don't even know what it is. It's over 100. Does that make sense?
Yes.
But 5 times 6 is 30, and that's what we need. Okay? Any questions about that?
No.
Okay. You also see where they came up with answer choice C, 36. They just added. This is why number slapping doesn't work, right? Like, 36. I've got a 30 and a 6. I'll just add them and see what happens. Oh, I got C. Okay, great. Yeah. I'll just subtract them, see what happens. Oh, okay, I got B. Great. I'll multiply them, see what happens. Oh, I got D. Great. But logically, we know the area has got to be smaller than the volume. It's got to be. It essentially always is. It's either A or B, and it's A. Okay? All right. Any questions about that, Jackson?
No, sir.
Nope. All right. Let's see what's next. Oh, we already got that. Oh, I recommend, by the way, whenever you see a word problem and you can draw a picture, draw a picture. I think it's very important. But you gotta know what a rectangular prism is there. But now you know. Question number 4. Go ahead and read this for me, please.
Robert sells 4 different flavors of jam at an annual farmer's market. The graph above shows the number of jars of each type of jam he sold in the market during the first 2 years. Which flavor of jam had the greatest increase in number of jars sold from year 1 to year 2?
Okay. Let's start with some graph analysis here. Okay, I like doing. I've got a method that I use for graph analysis. I tell students always start with the title of a graph, Notice there's no title here, sadly. But I always start with the title. If there's a title. Then start with the y-axis going up and down. Then the x-axis going left and right. Study those. Look for a key if there's a key. And we got a key right here between year 1 and year 2. And then lastly, look at the data. Lastly, look at the bars and the points on the chart. Lastly. And then you can draw your conclusions. Does that make sense?
Yeah.
Okay, so there's no title. There's no title here to this graph. Let's start with the y-axis going up and down. What's the y-axis going up and down?
Excuse me, I didn't hear that.
Yeah, what's the y-axis going up and down on the chart? What's that signify?
I'm not sure.
Well, it tells us this is the y-axis going up and down.
Okay.
And what's it tell us that is?
Oh, it tells us how many jars were sold.
How many jars were sold, exactly. The jars sold. And then also notice the range. Because it ranges from 0 all the way up to 40. But it looks like the biggest value here is 35 on the chart. But nonetheless, from 0 to 40, jars sold. And then on the x-axis, going left and right, what do we have?
On the x-axis, we have all the flavors.
The different flavors. We got blueberry, grape, peach, strawberry, whatever. Okay, great. Is there a key?
Is there a key?
Yeah, a key. You're familiar with the term a key when we're talking about like graphs and charts?
I'm not sure.
Yeah, so key is, it's this part is the key right here. Oh, I want to erase.
Oh, yeah.
Right.
Yeah.
This part is the key. It's like where they tell you what the specific data points, what the specific bars signify. Yeah, it's just like a, yeah. It just helps you interpret the data points. And so the dark or the light gray is year 1, the dark gray is year 2. Okay. Now, lastly, let's look at the data. Okay, don't even worry about the question right now. Let's just look at the data on the chart. Are there any trends, or can we see any conclusions we can draw from this chart?
We can say that strawberry had the greatest decrease. No, strawberry didn't have the greatest decrease, but grape had the greatest increase from year 1 to year 2.
From year 1 to year 2? What was the increase?
Yeah.
What was the increase in grape from year 1 to year 2? What was the increase?
30.
No, that was not an increase of 30 jars.
No, it was 5.
That's an increase of 5.
Yeah.
And I'm looking at this graph, and I see an increase bigger than 5. I see an increase bigger than 5. Don't you?
Yeah, with blueberry.
Blueberry, man. Blueberry, right? I mean, here's an increase of 5 right here. Blueberry's got a bigger increase, dude. Look at that. What's that increase?
It's like around 5, 6, 7, 8.
8 jars, man. 8 jars. I'm looking at strawberry now. At first, I think you said strawberry had the biggest increase, but strawberry, that's a decrease of like 15.
Yeah. I was just thinking out loud.
Yeah, no, you're good. You're good. Does that make sense? Why?
Yes.
Even though grape sold more than blueberry. Yeah, absolutely. The biggest increase is in blueberry. Does that make sense? Which I think is the exact question. Were you looking at the question or no? Were you just looking at the chart?
I was just looking at the chart.
That's funny, because like we basically answered the question. Because look at the question now. Read that last sentence.
I mean, I read the question.
Yeah. I forgot what the question was asking us to solve for. But just talking about it with you right there, I mean, we solved it. So, was it blueberry? Any questions about that?
Nope.
Okay. And really here it's almost like a reading question. It's like it's not which had the most jars. A lot of kids are going to pick grape. Yeah, they sold the most in year 2, but that's not the question. The question is which had the greatest increase, and that's blueberry. Okay. All right, I really recommend using that method of title, y-axis, x-axis, key, then lastly look at the data. I think it'll help with the accuracy of your interpretation of graphs and charts. And we'll see some more of those too coming up later. Rates, yes, rates. I like this question a lot. Go to question number 9 for me, please.
Water runs from a pump at a rate of 1.5 gallons per minute. At this rate, how long would it take to fill a tub with 150-gallon
capacity? Yeah, capacity.
capacity?
What's that mean? It's got a 150-gallon capacity. What does that mean?
That's a max.
That's a max, exactly. That's how much it can hold. Maximum, exactly. Okay. All right. Now the temptation here again is like, oh, I see two numbers. I know I'm supposed to do an operation. You know, like what am I? Am I divide? Am I multiply? Am I add? What am I going to do? You know, like I'm not even worried about that right now. Let's think about this logically. Let's do some basic estimation. Okay? Can you talk me through this one, like estimation-wise, Jackson? Like,
yeah, I think so.
Yeah, let's talk me through this one.
Okay, so it gives us 4 answers to choose from, and it gives us that we get 1.5 gallons per minute.
Yeah, exactly. Okay.
In 10 minutes,
yeah,
we're not going to have 150 gallons.
Yeah, how many? In fact, we can figure that one out logically. If it's 1.5 gallons per minute, how many gallons am I going to have in 10 minutes?
You're going to have 150. Wait, are you?
I don't know. That's what I'm asking you.
I think, no, you're going to have 15.
Like 15, right? Because like if it's just 2 minutes, it's going to be 3 gallons, right? In 3 minutes, it's 4.5 gallons. In 4 minutes, it's 6 gallons. I'm going up 1.5 every time. 4 minutes, 6 gallons. 5 minutes, 7.5 gallons. I mean, basically 15. Now that I see, okay, yeah, it's just 1.5 times 10. Right? Does that make sense?
Yeah.
Yeah, A's gone. And we can just feel that one out. Again, just basic estimation. Don't worry about the operations. Just feel it out. What about B?
I would say B would be the answer because we see that A, it just goes up to 15.
Yeah. Yeah, if we multiply by 10 and we get 15.
Right.
Yeah. And that's it, man. Yeah. That's it. It's A. Done. If multiplying by 10 gave us 15, multiply by 100 is going to give us 150, which it is. Does that make sense?
Yes.
Good. And this is why number slapping just doesn't work. Like, so many kids are going to multiply. They're going to be like, oh, I got 150 and 1.5. I'll multiply those two. Oh, I got 225. There we go. No. Just feel it out logically, man. Feel it out logically. Which you did beautifully. Beautifully. Any questions about that, Jackson?
No.
Dude, take this to after. If you can approach questions like this, take this test soon after we finish the course. While this approaches.
Are these about as hard as the questions get? Or?
We're gonna get to some algebra. No. This is I'm working. We're working our way up level of difficulty wise.
Okay.
We're working our way up.
Some questions will be on the test.
What's that?
This type of question will be on the test.
But this type of absolutely will be on the test. Absolutely. Yeah. We're still on day 2, of the course.
Yeah.
But this is a big chunk of the questions are just like this. Yeah. Okay. But again, I'll show you how to even the algebra. There's just not that much algebra you got to do. I'm going to show you all the tricks for that one. Okay. But again, it's like a way of looking at the questions that you can do that. Go and read number 13 for me, please.
It took Khaled 90 minutes to complete 40 tasks. Which of the following is an equivalent rate?
Ooh, okay. What does equivalent mean?
Equal.
Equal, absolutely. So we got to find an equal rate to 90 minutes and 40 tasks. I like thinking in terms of like tasks per minute, not like minutes per task. Right? I think like he can do 40 tasks in 90 minutes. Right? I think that's a little bit easier to digest. Does that make sense?
Uh-huh.
He can do 40 tasks in 90 minutes. Which is, if you're going to estimate like roughly how many tasks per minute that is, or how many... roughly, what is that? I mean, is it less than less than a task per minute, or more than a task per minute? Is it less than a task per minute or more than a task per minute?
I don't know.
He can do 40 tasks in 90 minutes.
It's definitely more than a task a minute.
Well, stop and think about it for a minute. He's doing 40 tasks in 90 minutes. 40 tasks in 90 minutes. Now, if you were doing 40 tasks in 40 minutes, that's a task per minute.
Yeah, so it can't be A.
Well, hold on just a minute. I'm not saying it is. I don't know what the answer is. I'm not sure. I don't remember. We're going to find out. But I'm still on the question, is this more than a task per minute or less than a task per minute?
It's definitely more than a task per minute, because if it was a task less than a task per minute, if it was 10 tasks in under a minute, then
don't worry about the answer choices right now. Don't worry about the answer. I'm just looking at this. I'm looking at 9 minutes and 40 tasks. I think that's less than a task per minute. I know it is. I know it is. Because if it was 40 minutes, then it would be a task per minute. Right?
Mm-hmm. Okay, so
But it's more like if it was 80 minutes, let's say it was 80 minutes, then it's easy. He's doing a task every like 30, or it's taking him 2 minutes to do every task. 2 minutes. Right?
Right.
To do every task. If it was 80 minutes. I'm just feeling this one out. Does that make sense why I can say that? If it took him 80 minutes to complete 40 tasks, we're talking he can do a task in 2 minutes. Does that make sense?
Yeah. Because if you didn't do a task per minute, yeah, I see what you're saying, yeah.
You see where I'm going with that? So we're talking about a little bit more than 2 minutes for every task if it's going to take him 90 minutes. Just a little bit more than 2 minutes for every task. Does that make sense?
Yeah.
Okay. All right. So we're talking less than a task per minute, like half of a task per minute, basically. So I can eliminate some answer choices here. What can I eliminate right off the bat? Now that I know we're talking about less than a task per minute.
I'm getting confused.
Yeah. No problem.
I'm looking at all these answers, and then I'm hearing like different variables.
Yeah. There's a lot going on here. Would it be helpful to come up maybe with a specific rate? Like how many tasks he's able to do every minute? Would that be helpful? Let's do that. Let's do that. Like if we're talking like miles per hour I'm not getting it. Let's talk about tasks per minute. Let's do that. Okay. So literally, if we're talking about rates, all you have to do is take the number of tasks, 40 tasks, divide by the number of minutes, and we'll literally get the number of tasks per minute. What's 40 divided by 90? This question they'd probably give you a calculator on. What's 40 divided by 90?
40 divided by 90.
Yeah. Use a calculator on this.
Yeah. It's 0.4444.
Yeah. So we'll say 0.44. 0.44 tasks per minute. Does that make sense? Oop. Hold on. I just realized I was off the screen there. 0.44 tasks per minute. Sorry about the wretched handwriting. Does that make sense?
Yes.
He's doing 0.44 tasks per minute, which is what I was saying earlier. He's doing less than 1 task per minute. He's doing almost half a task per minute, but less than half a task per minute. Does that make sense?
Yeah.
Okay. If it was 80 minutes, he was doing 40 tasks, and then it would be half, 0.5 tasks per minute. He's doing a little bit less than half a task per minute. Okay.
So that's why it takes him 90 minutes.
Yep, to do 40 tasks. Right? He's not doing 90 tasks in 90 minutes. He's doing less than a task per minute. Does that make sense?
Yeah.
Okay. Now I'm looking at the answer choices, and I know I can eliminate some that just aren't. In fact, they're more than a task per minute. Right?
Right.
Which ones are more than a task per minute?
Wait.
Look at answer choice A. Let's start with answer choice A. Is that more than a task per minute?
No, that's way less.
No, that's way more. Think about it. He's doing 10 tasks in less than a minute? He's doing 10 tasks in like 50 seconds or something like that. 55 seconds. For answer choice A.
But we see that 40 divided by 90, that's 0.44 tasks per minute. So I didn't... Can he do that?
Well, look at answer choice A. We're talking in 1 minute. He's doing 10 tasks in 1 minute.
10 tasks.
In just about a minute. Yeah, let's just do some estimation here. Don't worry about 0.9. I think that's throwing you off. Answer choice A is saying he's basically doing 10 tasks in a minute. Let's think in concrete terms. Instead of like tasks, let's say like, we're saying like folding shirts. Right? He's folding 40 shirts in 90 minutes. Does that make sense? Maybe make it more concrete. Maybe that's helpful. Okay? Does that make sense? Let's say you can fold 40 shirts in 90 minutes. Okay? Are we good?
Yes.
Okay. Do you think, if he's able to fold 40 shirts in 90 minutes, do you think he can fold 10 shirts in 1 minute?
No, I don't.
No! No way. Right? Because he can fold less than a shirt per minute. So there's no way he's going to do 10 shirts in a minute. That's crazy. Does that make sense?
Yes.
And now I think, honestly, the biggest deal is like, we just need to make it concrete. We just need to make it concrete. With an actual example. There's no way A is going to work. Okay. Let's test answer choice B. Now we know he folds 40 shirts in 90 minutes. Do you think he can fold 10 shirts in 2.5 minutes?
10 shirts in 2.5 minutes?
Yeah.
No, I don't.
No. He can't do 2 shirts in 2 minutes. He can do maybe 1 shirt in 2 minutes. But he can't do 2 shirts in 2 minutes, let alone 10 shirts in 2 minutes. No way. Does that make sense?
Yes.
Okay,
that
good.
Makes sense.
Good. Well, I think the most helpful thing was to think in terms of an actual tasks and what might actually be possible. Does that make sense?
Yeah.
I think that's the kicker here. Again, you've got to make this concrete. You've got to make it real. And then the logic you can feel it out. Can he do 10 tasks in 9 minutes? Well, 9 minutes is almost 10 minutes, right? No.
Because you can't do a task a minute.
No.
So
Yeah.
Yeah.
Yes. Now you see where this is going. Is this making sense?
Yes, this is making sense now.
Good. I can tell. C's gone. And really estimating that too. Rounding that really helps, right?
Right.
Like turn into 10 minutes, roughly. Because it's basically 10 tasks, 10 minutes. That's a task per minute. He's not doing a task per minute. He's doing less. He's doing less than half a task per minute. He can't do 10 tasks in 9 minutes. That's more than a task per minute. That's more than a shirt per minute. He's not even doing half a shirt per minute. No way. What about D?
D is definitely correct.
That might work. Could he fold 10 shirts in 22 minutes?
Yes.
Oh, yeah, that works. That would work pretty well.
And we see it took him 90 minutes to do all of those tasks. So it couldn't be C because 9 times, it's not.
Yeah, basically, if we multiply everything by 4, right? If we multiply 10 tasks by 4, we'll get 40 tasks, right?
Right.
So if we multiply the minutes by 4, we should get 90. And I think we get closer. We do get exactly that with answer choice D. Multiply 22.5 by 4, we get 90. Okay? Any questions about that?
No, I see that.
I love, and by the way, this is why I'm so glad we're working on this together. I'm not just like explaining it on my own. You know.
Yeah.
Is the takeaway there is okay. Come up with a real concrete example of an actual task and see what's reasonable. Right. He can park 40 cars in 90 minutes. Okay, he's like a parking attendant. Right? Imagine that. Okay, he's pretty good. He can park 40 cars in 90 minutes. Okay. Could he park 10 cars in a minute? No! It doesn't even sound right.
No, that would be crazy.
The crazy. 10 cars in a minute. Can he park 10 cars in 2 minutes? No!
That's a good way to think about it.
Right? You got to make it concrete. That's the takeaway. Does that make sense?
Yes.
There you go. It's not a math test, dude. Yeah, the math principles. Make it real. Okay. We're going to take a break here in just a minute. Do we do rates, conversion units? Boy, oh boy, oh boy. In fact, let's take a break right now. Let's take a break right now because we're going to introduce a new principle coming up, conversion units, and then and we'll go from there. Okay?
Okay.
All right. Take a break, and I'll see you in about 3 minutes.
Okay.
All right. Thanks, Jackson.
Thank you.
Bye.